feet on there.
Yeah. It's pretty subtle, actually. Okay, so I'm going to be talking to you about new optical properties of silicates and how we derive them. But first I want to talk just way too ambitious. A little bit about why we want this and why it's really important. So most of the dust that's out in space is going to be either silicate or soot, more or less. We don't know the exact structure. That's basically what I study. But in order to be able to correct for it or to try and use it in models to understand what's out there, you really need to have good analogs of the dust in order to put them into models to be able to model either your extinction due to the dust or to be able to see what should my spectrum look like. If my star is surrounded by this sort of dust, what would my spectrum look like? And so we've been doing infrared astronomy for about 50 years, and we've got data on all sorts of dusty environments, and about maybe 30 years or so, maybe 40, people started to do lab experiments to try and get data on analogs of the dust. And so you take spectra of it, you look and see what does it look like. But if you want to put it into a model, say a radiative transfer model, then you actually need to have it over a very large wavelength range. And that's a problem for similar reasons to why we have problems doing large wavelength ranges in astronomy with one instrument. You just can't do it. You're not sensitive over a big enough range, right? So you'll take a spectrum of something in the X-ray region and in the far UV and in the near UV and in the visible and in the near infrared and the mid infrared and the far infrared, and those will all be different detectors, okay? So one of the things that people have done in the past is to basically try to kludge data together. So there's quite a lot of data on what minerals look like in the mid-infrared, but then trying to get something that you can then say, okay, I want to put all of these data together. So what we're seeing here is, this is actually on the y-axis, this is the K is the imaginary index of refraction, but that's basically the absorption, okay? We can get into the semantics of it, but it's basically the absorption by the dust. On the x-axis, it's just wavelength in nanometers. And what I've got here is, in this panel, this is showing you, they're all the same limits, they're all starting from about 200 nanometers and going out to 1200, so near UV out to near IR, okay? And in this panel, it's showing you the data that most people use when they're trying to construct, say, radiative transfer models. Because this is the stuff that has a really good broad wavelength coverage, okay? And what we've got is the most commonly used is actually this one that has the X's. And this one is from Drain and Lee, 1984. And this is the one where they actually very carefully put together, they found pieces to put together all the different wavelength regions and came up with this particular set of data. But there's also these other ones, for instance, these two up here are also derived from taking both laboratory data of real minerals and observations. Drain and Lee also did this. Now, the problem here is that what they're doing in the mid-infrared, they're not using real minerals, they're using astronomical data and using that to say, oh, I've got a spectrum of an object. Actually, it's an average over about 500 objects. I've got a spectrum. This is kind of what my spectrum should look like in the mid-infrared. That's what I'm going to make my optical constants do. And that's what it does in the mid-infrared. In the near UV, over this end, what they do is they take real data. So they've got real data, but not of necessarily the same mineral that they think is causing the problem, which I'll come back to. You also have data that people have taken of real minerals completely, but then you have wavelength coverage issues. So you can see here, I know you can't see all the legends, but these are basically all very similar silicate materials. And you can see here, this one, it just stops somewhere in the visible. You don't have data out to this end. So you don't have enough data to actually be able to model properly. Likewise with some of these, you also have issues of what's in the sample, that often they were done long enough ago that issues of impurities were not well understood. Let me try and put that into perspective for you. If you have aluminium oxide, Al2O3, and it has chromium impurities in it, it will be a ruby. If it has titanium impurities in it, it will be a sapphire. The impurities are actually really important for the optical properties. And so one of the problems with some of the data that is plotted on this side of the graphs is that they're not well characterized, and so you're not quite sure what you've got. And like I say, this comes from astronomers not fully understanding how minerals work. And this is going back far enough that that's somewhat understandable. So what we tried to do was basically say, okay, we can make a sample, we can make enough of it that we can do the same sample that is chemically homogeneous for all wavelength regions. And so we know that we have got exactly the same sample throughout our wavelength regime, instead of it being, oh, well, this bit here comes from astronomical observations. This bit here has just emerged into this bit here, which is from a crystalline material, and so on. We have the same material throughout. Okay, so that's kind of the motivation, is to put something out there that's real and that is, the same thing all the way through the spectrum. I just want to say what the sample is that we're going to look at. So one of the things is that the classic features that we see in the infrared, and I know most of you have seen these before because we showed them ad nauseum, is this big, smooth 10 micron feature. So you have a feature that basically looks something like this, where this is around 9.7 microns, okay? And it's a big, broad, smooth feature. And this is attributed to some sort of amorphous SiO bearing solid. So you've got, this is given by an SiO bond, okay? But if it was a crystalline material, you wouldn't get something that looks like this. You get something that looks more like that, okay? It's because it's amorphous, the bond lengths are variable, so you get this merging and you get all these different things coming together. So what we made, this was actually made over in geology in a lab that plays with lava. This sample, we've got the composition here, and this is how geologists like to quote the composition of rocks, is in terms of the oxides that go into it. But this is our sample. It has a very small amount of water in it, which we can account for. It has no iron in it. There's a couple of reasons for that. One is that it's actually really difficult to make it a glass, something that's amorphous, if you put iron in it. If you put iron in it, it really wants to crystallize. And so just from a purely practical point of view, it was very hard for us. We've actually done more experiments more recently where we've got some with iron in. But just for purely practical reasons, not putting iron in was useful. But there's also a lot of theoretical models for dust condensation that suggest that iron should go into metallic iron grains and not into the silicate. And so there is some good astronomical reason for doing it as well. But basically what we tried to do was to say, get the relative abundances of the cations. So we've got the Si, the Al, the Mg, the Ca, the Na. They are all in the same relative abundances as for the Sun. Okay, so this is solar composition. Once we get down below those particular constituents, the abundance drops off low enough that we don't worry about them. Okay, so this is something that has solar composition except for the iron. It is a glass. That is, it's got amorphous structure, and it is in a large enough sample that we can then do lots of experiments on it. Just little things here. One of the things that the lab over in geology does is to study how the glass behaves around its melting point. That's actually the point of the research over in that lab, is to study lava for volcanoes. And so we also have some really good data on the physical properties of it, including its glass transition temperature. So what this means is that if it's heated above 1001 Kelvin, it will crystallize. Now, you have to be a little bit careful about that statement because there's a time scale issue. But if you heat it above that temperature, it also means it has to be cooled below that temperature very fast. And that's the issue with crystallization versus getting the amorphous states. Okay?
So how do you determine this chemical composition? So you put say 10% on salt, giving 12% on
Yeah, it's actually done. It's actually done this way. So you make it, and because you're making a glass, you basically put all the constituents in, and then you melt it. It's all these oxides which you buy.
Solid phase
they're solid phase.
And then put in the lab.
They're put in the lab. They're melted. So it's not done in the way that, say, Joe Knuth, who's over at NASA Goddard, does these experiments that are like vapor deposition things. This is much more controlled. We have much more control over what's forming. So basically, you melt it and you stir it and you make sure that you get something homogeneous.
And the first dance, then you make this material.
Right. And then you can analyze it to make sure. So we've done using a lab out of Wash U. We've done analysis on the composition. So we know that the composition is what we wanted it to be. Okay. Okay. Now we already had infrared data on this a couple of years ago that we'd already published, but we now have the ability to do UV visible. And what I mean by that is everything you can do before you need a vacuum chamber. Once you get below basically about 200 nanometers, it's actually 190, you run into issues of what happens with the atmosphere. And so you can't do below 190 nanometers without going to a vacuum chamber. But we can do 190 nanometers up through, actually all the way through the visible to the near infrared. So we can do spectroscopy that takes us up to about 3 microns, and then that overlaps with the infrared that takes us 2 through 25. And then we also have far infrared, which takes us out to 200. And this is just for people who are lab nerds that really want to know about this stuff. This is Carly, who some of you have met. She's the one who actually did the experiments. And this is, and I'm going to get into the issue of what we're actually measuring, because this is where trying to make sure that we're comparing like with like. One of the problems that I found, and I teach some of this stuff in one of my courses, and one of the problems is the language that we use in this particular field is you have mass absorption coefficients, ideal absorption coefficient, volume absorption coefficients, absorptivity, absorbance, and so on and so on. And it's very easy to get confused about exactly an opacity and all that. Which one are you actually talking about? And people will actually use different letters to mean the same thing, or the same letter to mean different things. And so I want to make sure that I know exactly what I'm talking about. The number of times I've gone through this is quite alarming. So I just want to go through this, which should be fairly simple. But basically, I want you to be considering, if I have a flux of light with some lambda dependence hitting a slab of material, my slab is dx wide, it has density rho, and the light that comes out the other side is not the same because some of it was absorbed. Then I have the flux f prime. Then I have a change in flux of df, and I can describe my df as being dependent on the initial flux, the thickness of the slab, the density of the slab, and its opacity. And here it's a little k, which is confusing because we also use k to mean the index of refraction, the imaginary part of the index of refraction. It's not the same k. Sometimes this will be kappa. Just want to point out where people make messes on this. In this case, I'm using k partly because I was having issues finding kappa in the equation editor. The new version of Word sucks. Okay, and then just taking that further, so I'm just going to integrate it. And so I get that how the flux is going to change depending on the thickness as it comes out the other side depends on the initial flux, and in fact that's the optical depth. Okay? So this is the experiment that we're doing, is we're actually making slabs. We do this with thin films, and we have good reasons for this. So we're basically doing a slab like this. We have light hits it. We know what the light is that hits it. We can measure the light that comes out the other side. Okay? And so if I go to, but it gets a little more complicated because this is showing you some of the things that have been missed in the past. So even people who've done some fairly good lab experiments, they haven't accounted for some of the things that happen in reality when you're passing light through something. So you've got a slab of material. You've got light hits the slab. You'll get some reflection and some passing on through. Then when it hits the other side, you'll get some more reflection and some passing on through. And so you have these two reflections that, if you're not careful, you will account for them as being part of the absorption. And that has been something that has come up in the past with overestimating the absorption by some of these materials. And so this isn't quite correct, which I'm going to get to in a second. And then you also have, where I measures this way, you have a reflection here, but you also have a reflection here. And this is where playing around with using different thicknesses of slabs can help you. If you have a fairly thick slab, you can have something where the absorption going through is thick enough that you don't get any bouncing back out. So for reflection, you actually want to have a fairly fat slab. Whereas for measuring the absorption as it comes out the other side, so we want to look at the light here and the light here. Measuring it come through this way, it needs to be transparent enough to get through light through. Measuring it this way, it needs to be fat enough that you don't need to worry about that. Okay? And that's another reason why being able to make a sample big enough that's homogeneous, that you know that it's all the same, so that you can actually do multiple pieces. You know, you make one big piece and then you break it up. Okay? So we've got, this is from that last slide. There should be a minus there. Good at typos. But basically, I measure I/O is that opacity, density, and thickness. And I'm translating this to A and D because on here it's D, because they didn't have time to fix that. And A is what we think of as being like the ideal absorption. I think the official term for that is the ideal absorption coefficient. But like I say, people play with these terms all the time. So if we were to take this and put in this and get rid of the logs, and the 2.3026 is just the conversion because this is log 10 and this is natural log, right? So that's what it should be, but now we need to account for the back reflections. And so what we actually get is we measure an absorption, but we also measure the reflections. So we do both, and then we can actually get the true absorption, and we can get out the reflection as well. And we do this with multiple things.
This is a true mover.
Right. So it's normal. It's normal instance. Yes, absolutely, and it is normal instance. Yes.
This is actually same sort of conceptual issue comes up in analyzing rigid parameters, and that's why a lot of elementary explanations turn out not to be right.
Right.
And you have to get to. We also have to think about the phrases.
Yeah. And it's something that, you know, we published this for silicon carbide a few years ago, but it hasn't quite caught on yet. So we have to keep publishing it. And this is just basically taking that a step further. So here we've got how we get the A lab out, but what we actually do is to take a bunch of samples, and we don't just do two. We'll do them as thick as we can get them and still get transmission, but we'll take them down to as thin as we can get them, so that we can get A out by just doing differences. And then once you've got that, you can quite easily work out, get R out from the R experiments as well. And so you can make sure that they're all compatible. You can make them thick enough that you get no transmission, but you just get reflection. You can make them thin enough that you get lots of transmission. And so we can get out numbers that we really trust. And we can do multiple samples because we make a big enough sample to do it with. And then we can get the, this is K, which is the imaginary index of refraction. And so this is fairly simply calculated. This is just frequency, and this is that A, the ideal absorption coefficient. And if you've got R and you've got K, you can get the real part. And so once you've got those, and this is all from measurement. There is no Kramer's chronic, there is no classical dispersion. This is all from experiment and doing multiple experiments on the same samples. And so we can get out really reliable N and K values for our spectrum. And like I say, we don't just do this for this one sample. This is the one sample that I'm talking about today. And so here what I'm showing is this top panel is the real part of the refractive index, and this is the imaginary part. And the inset just shows you basically the little bit up here. It's actually this little bit right here. Just the very inset bit, because you can't see it otherwise. And what you'll notice is that the place where it makes the biggest difference is in the UV. It's really, well, in this visible UV zone right here. But the biggest difference is, you know, we still get a feature around 10 microns, and we still get the same overall shape, but it's not quite the same. And you can see especially here, the absorption here in the visible out to the UV is much, much less. Now this was known. The data that's up here, so the blue and green, actually you can't see the blue because the blue and green are very close together. The green is Drain and Lean 1984. That's the set of optical constants that everybody uses, okay? Because it was done well and it's very easily available. The blue is actually the same data tweaked a bit a few years ago. It's about 10 years old now, that data. And when it was put together, they knew that there wasn't enough absorption in this zone, and so it's actually fixed to be this high. That doesn't come from real data. It's fixed to be that high. But what that means is that when you use those optical constants, you don't know what you're actually putting in. It's already faked, right? And so what our data does is allow you to use a real thing. It may not be the right real thing, but it's a real thing. What we're hoping is that we can apply this same method to a whole bunch of other samples. Like I said, we now have some iron-bearing ones, but they haven't been spectroscoped yet. Sorry, go on.
Okay. So how does it compare with the other amorphous sample? Experiment sample.
You mean with like the ones that come from? Well, the problem is that most of those, the Jena group's data though is typically extrapolated. So they do. So it compares. We can compare. No, this is the problem. We can compare in the infrared, and we can talk about. They're very similar. It's not an issue. And especially since they use a similar method, they do basically melting and a splat quench, which is what we do. So they're very similar. They don't do exactly the same composition, so they're not exactly the same. But compared to their enstotype, for instance, it's very similar. But they only go down to 2 microns, so we can't compare at that end. And that's again one of the motivations for us doing this is to produce real data all the way down. And so this is then taking those data and calculating the absorption cross sections. Actually, it's Q, so it's grain size independent. And you see the same thing. That basically you've got something similar, but the absorption is less throughout, and especially here. Like I say, it's iron free, and we've known for quite a long time that we probably need some iron in these grains to get the absorption up. What we haven't done yet is to actually prove that. That is.
So the non-famous opacity now what that actually 10.
Oh, it's hugely lower, and you'll see as I show you some models. It's killing me to model this stuff because now I need to have my optical depths up at ridiculous.
So the previous mass estimations are now underestimated by that one.
Right.
So this is very.
It's a big deal.
The feature is also much shorter.
The feature, yes, it's actually hitting this side, but not this side. It's like the feature that you see that was used, and nearly all of them actually use the same data. It nearly all originates from the Vulcan quark work from like the 80s. It's nearly all actually from IRAS data on AGB stars is where that shape comes from. And so if you look at it, it's too broad, but I think that's because it's an average. And so you get this weird averaging out, and so you get this broadening, and so what you get is it's broader on this side. And actually, we published a paper. This is the Speck, Whittington, and Hofmeister paper. That one we showed that all of them are way broader than real silicates, except for some really obscure things. Okay, and so this is, like I said, we may not have exactly the right thing, but we can at least.
So the now opacity by infrared. How does the affect sensitivity of iron? So here you don't have.
We don't have any iron. I don't know that I can answer that. So we have samples now. This is actually a project that. So Whittington is my other half over in geology, and one of his students is doing this for his thesis. And it's actually really hard to do because one of the problems is in silicate. So if you've got olivine, you have Mg2. SiO4 is the Mg rich end member, and Fe2 SiO4 would be the iron rich end member, but it has to be 2+. it's really, really hard in the atmosphere of the Earth to make it stay 2+. It wants to become 3+. So we don't have the data. I can't answer the question. Alex has managed to make some samples, but it hasn't gone out to St. Louis to do the spectroscopy yet. But then we'll have it. And we'll know exactly what the dependence is, because he can't go, I don't think he can go beyond about 50% iron, but he's got a 10, 20, 30, 40. So we will, hopefully, get that answer.
I guess it could be no.
Well, we'll see. I mean, I really don't know which way it's going to go. But let me just now spend some time talking about the application. I apologize for this figure. I didn't have time to remake it before this. Basically, this is just a log-log plot of HD 161796. This is a classic protoplanetary nebula. So this is something that it was an AGB star. It made lots of dust. It stops making dust, and the dust starts to spread out. And the central star is shrinking. The central star is actually, this is basically the black body of the central star, and this is the black body of the dust. Okay? And so what you've got is a central star that's much hotter than an AGB star. It's about 6,000-ish Kelvin. And then the dust is much cooler, around 200 Kelvin. Okay? And this is all collated data. I didn't take any of this data, but this object is pretty well studied. And we chose this object for several reasons. One is that once you get to the planetary nebula phase, you have enough ionization. You're talking about things where the central star is 30,000 Kelvin on off. You're ionizing the hydrogen. You run into issues of photoionization, which makes running models with it much more difficult. Okay? Then you have to actually be able to put this into a photoionization code and not just a radiative transfer code. Okay? Whereas this one is about 7,000 Kelvin, so we can ignore that. And so it just makes it a little bit simpler for me to model it. It's also something that there are HST images of it, and it's more or less spherical. So doing it in one dimension for simplicity is not a really horrible thing to do with this object. And like I say, there's lots and lots of data on it. And it's been modeled, and basically the dust out here has been modeled by various different people, and usually people include crystalline silicates and ice, but it's dominated by some sort of amorphous silicate. For our purposes, we're going to mostly ignore anything but the amorphous silicate and just see how good we can get. Okay? Now, this is a really busy view graph, and so ignore all of that for now. Okay? Let's concentrate on this upper left? Yes. Diagram. So this is basically, it's a linear plot with the inset being a log of exactly the same thing. It just helps you to see it properly. And what we've got is, you can see the points here. This is the data that we're fitting. Actually, it doesn't show up very well in this view graph, but there's the spectrum in there too. What the grey line is here is the best model I could achieve with the original Drain and Lee. And I can model it quite well using Drain and Lee's silicate. Okay? And then here I've got different models that have been made using ours, where I have to model it with the Drain and Lee silicate, I have an optical depth in the visible of about 2. To be able to model it with my data, I'm up in the 100 range. It's insane. And so my models are really slow, and so I haven't gone as far with this as I would like. But this is basically showing you that we're not very sensitive to the thickness of the shell. So this is basically the difference between these models is how thick is the actual shell. Is it a very narrow shell close to the star, or does it have a much further outer radius? And it doesn't, you can see it makes a little bit of difference, but it's not a huge amount of difference. But I also can't get it to be the right shape. It's not making this shape, right? If we move over to this upper right, in this case, they're all still the high optical depth, but now I'm looking at the effect of the drop-off in density. So if you just have constant mass loss rate, then your density distribution should be 1 over r squared. Okay, that's just, as the material flows off, you should naturally get 1 over r squared. You could potentially have decreasing mass loss rate, in which case you would have it go off slower than that. And so what we're modeling here, to try and come back up to this level, we're saying, okay, I'm going to include, this is 1 over r squared, this is the blue one. The red one is 1 over r to the 1.5, and this orange-yellow is 1 over r. And you can see that it really doesn't help me a great deal. I'm still playing around with all these parameters. The degeneracy in these models is pretty big.
The bracket box is also ratio.
Yes, yeah, and actually the spectrum is on there. It's just so faint that you can't see it on this particular view graph. I need to make them look better for these purposes. So then another thing that has been ignored in the past, you'll see here it says no ISRF, and it says it here as well. And these ones all have the same thickness. These are all the same size of shell. So what happens if you mix them up? Well, no. I'm saying you can get into an infinite space of different parameters you could use. But this one we actually included some interstellar heating. So the idea is that when you've got a really big dust shell, the star is able to heat the innermost dust, but the outermost dust is far enough away that actually you've got a lot of UV photons in the interstellar medium that you'll heat the outermost dust by the interstellar radiation field. And we can model that. And that doesn't, and I was thinking, well, that might help with this bit. But it doesn't seem to. I'm still playing with it. But it doesn't seem to help me very much. It may be that I'm not big enough. It may be that this is too small, that I have to make my shell much bigger to make it that have an effect. And then, and then this one I included phosphorite, which is the Mg2SiO4. It's crystalline, because there is a feature in the spectrum that bumps up here and it bumps up here. But just adding in a little bit of phosphorite, and this is 1% phosphorite. Just adding in a little bit of that, I can see it, but it also reduces my emission even more. Phosphorite is even more transparent than my glass, and so I have to increase the optical depth to get this to come back up. Okay. So far I have not succeeded in actually making this happen, making it model. What I think is going on has to do with the assumptions that were made when, for instance, the Drain and Lee, and this applies to all of the stuff that uses observations to derive the optical constants. So what they're doing is they're saying, okay, we've got some observations of, and it's actually a set of IRAS that they're using. It's an average over a set of IRAS. So you've got the set of observations, we've got what the spectrum looks like in IRAS. We want to reproduce that. But you have to make some assumptions. So for instance, in the original Drain and Lee, they assume MRN, which is a specific grain size distribution. What if that's wrong? I don't think that's going to be a huge issue, but what I think is an issue, and I'm going to have to draw this because I didn't have time to make it as a slide. Ooh, purple chalk. Somebody left this here for me, didn't they? Okay, so we think of there being a dust shell where you've got the star, and then at some distance from the star you have dust forming, and then the dust density drops off, and if it's 1 over r squared, it's going to go down like this, right? And let's just assume it is 1 over r squared. But now it's going to hit the interstellar medium. You think about how we think about our own solar system. It's moving through the interstellar medium, and there's a bow shock, right? What happens if, as the material that's flowing off the star hits the interstellar medium and piles up? This isn't new. This was something that when IRAS data images were first analyzed, far infrared images were first analyzed, these were papers from the late 80s that were basically saying, I think that we should model it like this. That we should have, basically a drop-off, but then an increase. I don't know that it's going to be sharp like this, but you should have some sort of increase at the outside where it hits the interstellar medium. Now let's consider that the data that was used to get the optical constants that generate this model wouldn't have assumed this. So it shouldn't be that surprising that I can model it with that data. Whereas with my data, I can't come close to that, and mine's real minerals. So I'm working on trying to figure out, the problem is that the degeneracy space on this is just enormous, and the options are enormous. I mean, where do I do this? How far out do I get before I have a bump? How big is the bump going to be? And so on. So I'm working on this, but I think that it means that the far infrared part of those standard optical constants that people use are not quite right because of the assumptions that were made in how they were derived. Does that make sense?
This is also because the opacity is 10 times smaller.
Right, that's true, but I'm accounting for that with the optical depth. I'm just putting in more stuff. I mean, for now, I'm not worrying about what the mass is. I agree that that's something that we have to worry about at some point. But at the moment, I'm just saying, okay, I'm just going to make this so that I can get a match and work out what that means then for the mass of the material.
So if the metallic ion is
So if it's metallic ion, if it's in thermal contact, well, I guess even if it's not in thermal contact.
just IRAS another dust component, and so then
Right.
They can help the photo part. And,
In Dusty, it would assume that they were in thermal contact because that's how it works. But yeah, I haven't tried putting in iron yet. Like I say, I was trying to do this in a way because radiative transfer modeling is inherently degenerate anyway, because what you're really modeling is tau, and so we've got these different things that counteract each other. You've got the thickness of the shell. You've got where's the inner radius, where's the outer radius. You've got which is basically in the dust temperature, and you've got the intrinsic opacity and the density, and so you end up with multiple ways to get the same answer, right? So I was just trying to avoid too many options. I agree. I think putting in iron is a good move.
No, you don't need to like runs water, let's say, in some component. I think they're just be separate.
Right, but the way Dusty works, it would assume, the way that, it has them in at the same temperature, which is effectively the same thing. So in Dusty is very simple. Given how long these things are taking to run, I don't want to move on to something more complicated because Dusty is quick. And it's already taking me, 30-35 minutes per model, and I've run about 1,000 of these so far.
Dusty doesn't work in, say, silicon carbide and the molten carbide.
No, what it does is it makes an average grain. It makes an average grain.
Only one
Yeah.
component.
Yeah, which is another reason why I was trying not to complicate it. Like I say, we did include phosphorite because there clearly is a feature that you can attribute to phosphorite in the spectrum. And I wanted to see what that does. What it means, though, I think, for the phosphorite is, you can see here, at 1%, you can already see it. I think it means that also estimates for how much crystalline material there is are overestimates because you always needed more to get it to be seen. Whereas with these optical constants, you don't need as much to be able to see it because this is already transparent. And it's to do with the relative opacity of the grains. And so I suspect that that there's an overestimate of phosphorite composition component in these shells too. And so
that is a data point at around 20 micron there, and it's sticking out.
Yeah, this one?
It's not going to. None of your curves are going through it.
No,
Does that matter?
Like I said, let me actually back up a second. You see how you've got like this here and this here. Let's see, it's that one?
Yeah, should be that one.
Yeah. So I can get it to go through basically all of this stuff.
Right. But
What about others?
That one is from stuff that Margaret Meixner did. So it's almost certainly.
so are you saying
Yeah,
that?
maybe.
Are you saying that those data are data?
Well, so there's a question here as to the variability of this object. Actually, remember this is in the log scale. Even here in the JHK, it's not exactly compact. So there is an issue that this object is possibly variable. So I haven't been worrying about it too much. I did try to dig into it and couldn't find anything. It's also possible that it's a crystalline feature, but I'm not going to
Well, it
go
seems
there.
like it's a mission line something. It's like a very sharp line structure.
But it doesn't show up in, so it, we have the, you can't see it on here, this only has the IRAS on it, and you can't, it doesn't show up well on here. I'll show you on my screen. We have the ISO, we have the SWS and the LWS, and it doesn't go anywhere near that point. Which is why I'm more convinced that it's a variability issue rather than a, AGB stars are inherently variable. This one shouldn't be, but there are some questions about that.
Probably I was thinking that.
I don't remember the basis for the periods of points that are vertical separate.
This is
in that previous
This is one that measure. Is that 21 micron? Looks like 21 micron.
This one shouldn't have it. This one does not have a 21 micron feature. It really doesn't. This is an ocean-rich object, and we haven't found that in anything.
Yeah, that's probably 16 to 15.
No, it should be longer than that.
No, it's right around
20.
it's right around 20. I can look it up.
Yeah, that is around 20. So it's just that that's not sticking out so prominently. I mean,
Right.
to my eye.
Yeah, I know. I was tempted to remove it, but that's cheating.
Well, you can put a very big
Always
arrow
on care always.
No, it's actually, so I'd have to look back at, so this was from a paper from Margaret Meixner. I'd have to look back at where it came from.
Yeah, so in your modeling, you didn't put out all the data points in this field map, right?
Right.
Maybe the IRAS spectrum.
There's at least 1 point, well, actually, they're all there on this one, but it got way too complex on here. And in the good version, you can see the spectrum. So, but I put them all on here, and you can see here it doesn't look nearly as bad.
Yeah, we call it take the log. Yeah.
But yeah, you can see from the spectrum that just seems to be an outlier. And like I say, I haven't figured out why that would be. Possibly a conversion error, but that's a whole other issue. You don't even want to go there with me. I think somebody should ban the use of magnitude. So anyway, this is, you don't have to read all of that. But basically, one of the things is just that we have this new data and it's available, that rather than using, the old data will work for you, but what does it really tell you? Given that it's derived from astronomical material. Ours is the only one that is available that covers the wavelength range. We do merge with other data once we get beyond 190, that is shortward of 190 nanometers, because we don't have the instrumentation to do it. But once you get beyond that, you're mostly into electronic stuff, and so it's fairly easy to model. And I think the biggest thing for me is, I don't know whether this is true yet, but I really want to get into this issue. That, yes, I can model with those old data, but if I can't do it with a real mineral, then what does that really tell me? And like I say, I'm working on coming up with some interesting profiles. If anybody has suggestions on how to limit the number of those that I can possibly come up with, that would be great. And that's pretty much it. Questions that you didn't already ask?
Well, at the risk of revealing I fell asleep there for a little bit, you were talking about spectra that would seem to be acquired from slab
Yes.
sort of geometries, and yet now we're talking about dust.
Yes.
And so what about things like knee scattering and other sorts of geometry effects on your data, which I know can yield substantial structure?
So, I think knee theory is, I think that using knee is a problem. Grains are not spherical. They're not. They're never going to be spherical.
But there are non-spherical knee theories. I mean, there are models that you can find.
And the problem is, I think, that we can do a great job of matching. Basically, you don't have big grain shape effects unless you have extreme shapes. So, if you've got a needle or you've got a pancake, then you're going to get some effects. But otherwise, basically, you're always going to have a distribution. So even though you might have, if you have aligned needles, yes, you're going to see something. But if you have something that is a distribution that goes from needle shapes to pancakes and is in any orientation, then what you get is an average out over that, right? And what you get from the slab matches what you get from real experiments done well with real grains, either by, there are some experiments that people have done by using levitation of the grains to keep them of quality spectrum. Some of it is done using KBR matrix, because potassium bromide is transparent in the infrared. You have to be really careful with that because it's easy to overload the pellet and then you get problems with opacity. But if it's done well, you get the same effect as levitating it, right? And then we can match we've already shown that works, that basically the shape effect is negligible. Now if you assume you have spheres, then you get something unreal. You get something that, unless the optical constants were derived from something assuming spheres, which does happen, you will get the wrong shape out if you use spheres, always. And if you use non-spheres and average over the grain, the different grains, then you get what we get from the slab. So the slab works. And trust me, we have done this a lot. Because you're not the first person to bring this up. We have to fight with people a lot. And the biggest problem is that what happens when you try to do it in that form, like say with the say using KBR, which is actually a standard technique in geosciences to do this. What happens is that it's very hard to do it well, and so you can get clumping of grains. So you may have characterized your grains really well before you put them in the pellet, but then they can clump, and so you may not actually have what you think you've got. If you put in too much, you get too much absorption, and then you get effects that have to do with saturation. And so you'll get features that aren't the right shape because you get saturation. But remember, you've got a feature like this, but it will become optically thick here before it becomes optically thick here. So if you get saturation, you'll get something that gets flat topped. Okay? And so what the problem with doing those approaches is it's much easier to fuck up, to be honest. But when it's done well, we reproduce what they get. So the slab seems to be, and what it allows us to do is then the sort of stuff that we're doing, which is really hard to do that method over the broad wavelength range. So you can make your pellet well for one regime, but maybe not for another. Because in the lab, you don't have the big column you have in space. So to get absorption in the UV, you would need to have thousands of those pellets put together to get the absorption you need. Does that make sense?
Yeah, I guess this is sort of a side question, but it's related to what you're saying. I don't understand why having the edge effect there, why does that change the spectrum?
Oh, because then what you're getting so when you're looking at the spectrum, so if you have that edge effect there and you have external heating, then you're going to get more emission from here than we do currently. So this is not an emission feature. This is just that if I've got more stuff right there, then I'm going to get more emission here. If I also have external heating, I'm going to get more emission too. So the combination of the two means that I can get more emission out in this zone. Does that make sense?
You're saying because that portion is cooler?
Not because it's cooler. So you can get your stars here, and you've got some heating from here, but the heating from here is not very strong. Remember, this is interstellar. But it means that your temperature doesn't drop off as much as you would think it would, and that extra temperature helps keep the far UV, the far IR, more than it would be otherwise. Okay.
Okay.
But then just having more grains, you've got more emission, and so that's really what I'm getting at, and that's how I think we can fill in between these models and what you get from this.
But the reason it doesn't just shift down the whole curve is because it's cooler out there.
Right. So you've
there's
still
only
got
one way
this
to
part
make it.
here is going to be dominated, but is going to dominate the near infrared, and this part here is going to dominate the far.
Okay.
That makes sense.
Yeah, that makes sense.
Other questions?
If you add IRAS, since plastic doesn't allow you to treat them and separately them from it.
I'm going to give it a go, though. I mean, because it's also just an intrinsic opacity effect. I may go to using 2DOST, which does allow you to do these things. It's just, it takes a lot longer to run because it's 2D. That's the next step, but I think trying to just show why our data is worth playing with is my main goal right now.
It's amazing, stress data works with this object. Here, when he divided the object constant, he basically from interstellar.
Actually, a lot of it comes from the stuff that Vulcan Quark did with IRAS data of AGB stars. Seriously? I've been back through that paper so many times, and it's like...
Not really. Because this stress data was published in 1984.
Okay, right now...
was found with IRAS. You mean the David Popular?
Right, it's the Ossenkopf and Henning one. The Ossenkopf and the other one, they have two, right? But yeah, no, but it's still based on astronomical
But this
observations.
is about jet.
This is strange, yeah, but I can do the same thing. I mean, I have models, so what I'm trying to do is show what's going to happen. So for people who have already done modeling with any of these data, what's going to happen, what do you expect to happen if you use real stuff instead of those data? And that's what I'm trying to achieve, is just get a feel for, okay, this is where your errors might be if we're right about this stuff. But, you know, like I say, at the moment my feeling is that I don't know what you learn from using those data if what you care about is the distribution of material. If what you care about is just modeling, you know, the overall spectrum and don't care about what the material is, that's fine. If you care about removing dust so that you can understand the star, that's fine. But if you want to actually understand the material that's going out there, I'm not sure what it does for you. Okay, I'm done.
Thank you.
Okay.